So I would like to have Dr. Vijay Sai start sharing the screen and presenting. So to give a short intro, he heads the Water Technology Center, which is the hub of R&D, digital and management for Larsen and Toubro in India, and especially into water and effluent treatment business. Previously, he was with Global Research Center of GE in Bangalore, associated again with water and effluent treatment technology. So, Dr. Vijay Sai, the floor is yours.
Is my screen up?
Yeah, your screen is up, and now you're audible as well.
Yeah. Okay, thank you very much. Yeah, sorry about that. First of all, thank you so much for having me here, and it's a wonderful forum to share some of the thoughts that I have. Thanks for this opportunity. And I'll straight away go into the topic without taking any further time. So this is a very interesting topic, something that I really enjoy talking about. Not that the outcome is very promising and it's very fancy, but definitely it's a time to wake up, and that's where this topic is so important today to be considered. Basically, I'm going to talk about the pollution and its impact. Everyone knows, but some other context to that. Why circular economy and how it is relevant to today's situation that we are in. Waste to value in the circular economy context. I just call it as an arc because it's not the total thing here, but it's important part of the circle to be considered for all our future endeavors. Then there are certain technology gaps that we've got to be considering, and we will conclude the talk very subsequently. So the picture that I am showing on the right of my screen is the technology center of L&T for the water particularly. So this is coming up in Kanchipuram. It's a huge facility that L&T is planning to put up with all the state-of-the-art facilities to study water, the technologies that are required to treat water, and also develop things that are relevant from the circularity standpoint here. So very soon into the next, interesting part here. I always find it quite amusing because it is always said 114 civilizations existed on the surface of this planet, out of which 112 disappeared, and only 2 continue to survive. One being India, the oldest one, and the other one is the China. There are many, civilizations that unfortunately we don't get to see here. For instance, this Eastern Island, Mayan, Anasazi, Akkadian, Ubar, and then the list goes on. That's plenty of list there, which unfortunately we don't see that. So basically, when we look into that, what has led to the disappearance of these civilizations, the factors that are responsible? Studies today, they indicate that the climatic change to be the prime reason. So droughts, the water level receding and the shifting in, the rain patterns and several other factors led to the fall of the civilization. But more importantly, the civilization did not adapt to the change, which was the main cause that is stated. And the climatic conditions changed, but this adaptation was missing, and that's why we don't see them, surviving today is one of the factors that is stated with all the research that is papers that are getting published today. Now, having said that, why it is relevant for us? Why should we be, in fact, caring about it? Because we are already having, we are witnessing that the trajectory as far as the change in climatic conditions are concerned. 9 parameters out of 15, or even for that matter, 10 out of 15. Global tipping points are being witnessed today, and which is definitely an alarm that we all have to wake up. That includes the rise in the sea level, the temperature, and the glacier melting, and several other factors out of 15 which are indicating that the climatic change is going to happen. It's happening. And then it is reaching a level, and that is contributing to the societal collapse. So this is the time that we must learn to adapt, because that's what we got to learn from the history. If we don't do it, that's a challenge. And at the same time, it's something that we are forcing upon us. Maybe in the past there were certain changes that happened which was natural. but this is the something that we are forcing upon us. And that's why it's all the more important to regulate before it is too late. And with that, message, I just wanted to quickly move into the next predictions that are coming from the past, because in 1970 there was an interesting publication that Alvin Toffler, a famous US writer, published. So how we as a civilization moved through different phases. We talk about the agrarian wave, industrial wave, and information wave, and all have happened in the past. Now we are in the information wave at the present. So the transitions have been, very interesting. Some took several thousand years, some happened in centuries, and the last one, the information wave, just took about a few decades. That's where we are in today. But the question is, that's all good. So what is in future for us? That is what we call it as a sustainable wave. Yeah, maybe the curve will plateau down, and then it will sustain, help us to sustain with all these things. But the way in which we have been exploiting, extracting, and misusing, abusing resources, will it allow us to stay there, or it will plummet? What is the future trajectory looking like? And that's where, another study that happened in 1970, around the same time, which we call today as the World 3 model, which is a dynamic model that was used for prediction of the fate of the civilization. This was a very interesting, outcome. What was seen that by 2040, the model predicted societal collapse. So it's after all a model. Why do we care about it? Why should we be thinking about it? That's not the case, because in 2020, Yale's journal actually published that most of the predictions that were seen until now are consistent with what has been predicted way back in 1970-72. Now, what does that mean? That means that if that is the curve, what is being shown here is a business as usual. That means that if we continue doing what we have been doing, the pollution level is going to rise, and the increase in pollution level is going to bring down significant changes as far as our population is concerned. You can see that 2040 onwards, it's going to get down. The industrial production is going to come down. The food production mainly is going to get affected. So all kinds of deleterious effects are going to be seen if we continue to pollute the way we have been doing. But on the contrary, if you look at the comprehensive technology, as a solution, that means that if we try to contain, the pollution here. Sorry about that. Let me see if I am able to get rid of the bar on the top, and then that's basically is going to give us some time to breathe, and then things will get settled down. That means that the main challenge for today is the pollution, and if we contain it, if we are able to bring it down, that's going to give us enough time to survive and then continue to happily live from wherever we are now. So that being the case, what should be our major focus? That's where the entire world is moving towards: the renewable energy, cutting down the carbon emission, and doing everything that is possible in the circular context, because we have been linear all along. We were very happy in terms of exploiting resources, take, make, and reject, and then we have caused significant damage, whatever was possible. Now, if we don't wake up, if you don't react, and then take up corrective actions, then the situation is not going to be conducive. So with that, we will just take a quick look at the situation we are in as far as the industrial water scenario is concerned, because the water is going to be the topic that I am going to talk about, and then I have kept it mostly restricted to the Indian context today. So when we talk about the water industrial scenario in India, I mean it's a known thing now. We have been extracting groundwater crazy. So 253 billion cubic meter per year is getting extracted, and we know that around 89% of the water that is groundwater is being used for agricultural purpose. 5% goes to industries and 6% for domestic use. But then what is the funny thing about it? The thing is that India is populated, 17% of the world's population is in India, but that's not the proportion in which the water is. We have only 4% of the world's water as resource now. Only we have 2.6% land there. But the way in which we have been using water, particularly the groundwater, is that 1/4 of the groundwater globally is being consumed just within India, and that is more than US and China put together. That's a very, very alarming situation that we are in today. Now, going forward, the industrial needs are going to improve further. So when we look at the overall industrial water drought in 2015, maybe it was around 10%. In 2050, that pie is going to increase further to 17%. Now, the industrial demand is going to get further up, and how do we meet that is going to be a challenge, and that is evident from the tariff. You can consider today. 1995, the Chennai water cost was around 12 rupees per meter cube, and today we have actually touched 55 rupees per meter cube, or close to 60 rupees per meter cube. And that's where it's all the more important to conserve water, preserve water, and then take the circular economy concepts into water deeply now, because the circularity needs to be integrated in every sense, because we cannot just talk about water. You produce, reuse, and recycle. That's not the only thing here, because we have to consider all other aspects associated with that. What is the energy that is required to treat the water, the nutrients that are going to be in water, how do we extract the nutrients out, and also from the waste handling perspective, how this could be dealt. So this is all the point which we have to consider in totality. Now, when we look into the natural hydrological cycle that the water typically follows, we have the rains, which are essentially the cloud formation happens through the evaporation and the trans evaporation of the through the trees. And then we have the groundwater, and also that is being used by the industries for household applications. The gray water is getting treated, and it's put back into the water resources. And this whole cycle by itself is circular in nature. So there is nothing that as far as water is concerned, and the natural path that the water takes is by default it is circular. So when we consider the interaction between the sink and sources, the circularity is guaranteed for the natural path. But when we to look into the managed cycle, particularly the human activities, when they kick in, then definitely this takes a different approach, because then you got to basically bring in energy between the sources and the sinks, and to make the water available at the required rate, in the required quality, and the required, with all the ingredients and so on. And then we have the waste that is getting generated with the treatment when the water has to be pushed back into the cycle. Now we got to manage the waste, and then so that's where the complete circularity, just from the water perspective, is not adequate here. So we got to understand what is the source of energy that we are taking in. As the previous presentation alluded to, the energy sources, right? I mean, it's very important that even the source of energy should be something which could be which guarantees the circularity. It's something which is renewable, and even the waste that comes out is something that has to be dealt appropriately. So this particular concept, what we are going to see is that there are sources and sinks, and the sources could be plenty, starting from rainwater all through the surface water, and then there are sinks, which are the industries, domestic, agricultural, whatever we can think about, and there is a water treatment and management system. And the water treatment system generates water, and at the same time there is a waste that is getting generated. Now the whole concept here is that how do we basically maximize the value out of the waste that comes out of the water treatment. In this context, I'm going to just focus the attention on water part, and the sludge that gets generated here, and the waste that gets generated here. How do we derive energy out of the waste and put it back into the system, so that whatever the energy requirements that we have, in terms of treating this water, can be basically met by the waste that is getting generated. So that's the decentralized circular economy concept of what we are getting to see now. And they basically rest on the four pillars that we can think about. They are basically the reduce, reuse, recycle, and reclaim. Now, reduce, as we have seen, is nothing but the makeup water reduction. You reduce the makeup or the fresh intake that you are going to have. Reuse is basically purposing the water for a different application. You repurpose whatever comes out of one unit operation, put it into another unit operation. That is a repurposing there. So you treat the water in such a way that it can be used again back by the same process from which it is getting generated, which is recycle. And if you can get any resources extracted out into the water, and also if the water can be sent outside the current loop for which it is initially was purposed, so then that becomes a reclaim part of it. So in this four R's, which define the circular economy context for water, I just wanted to share that, how we in L&T we are essentially looking into it. And the focus, what of this talk is particularly on the municipal wastewater treatment and the context that is relevant to India today. So what is the Indian context as far as the sewage treatment facility is concerned, or the sewage treatment plant operations are concerned? The municipal wastewater is getting generated, and that is the tune of about 72,000 million liters per day of water is getting generated. So we have an installed capacity of not equal to 72,000 MLD, but only, what you can think is around 31,000 MLD. And the operational capacity is only 26,000 MLD, and actual utilization today that's happening is only 20,000 MLD here. So there is a big, gap that is there in the amount of water that is getting generated today, from 72,000 to all the way up to 20,000, which is the actual installed capacity or utilization that we have today in the country. So only 26 to 28% of the sewage water that is getting generated now is being treated and is made discharge friendly. So that's a very challenging situation for a developing country like India, because you got to basically go 3 times more in order to meet the situation that developed countries in fact have. So that is a state-wise contribution. The next chart provides which state is contributing, and as you can say, the developed states definitely are contributing more towards the treatment, be it Gujarat or now Uttar Pradesh, interestingly, because of the Clean Ganga mission that we are getting to see there. Of course, Maharashtra, is able to generate quite a lot of water here. Now, as we talk about increasing this demand of treatment or treating more water towards the dischargeable standards, then definitely that brings in, where are we going to get the energy for the treatment? And as you can see, maybe the energy that we are spending today perhaps is very insignificant because of the capacity being limited. But when we look into the developed nation, for instance, US, around 3 to 4% of the energy is being used for the treatment of water and wastewater, and also to transport the water, of course. So there is a significant amount of energy that we got to use in terms of the treatment, and as we try to increase the capacity overall, we got to in fact understand that what impact it will have on our energy production and energy utilization. So that's the point which we need to be a little careful about. So coming to the capacity addition, we need to in fact plan that what is the stress it is going to have in terms of the power production and distribution, and how are we going to basically maximize the overall efficiency of the plant. How are we going to use the current capacity of the plant to get that adequate energy? Now, I just wanted to draw your attention on a representative, chart here, which talks about the various operating costs associated with the STP. For instance, when we look into the various parameters, there will be testing facility, the laboratories, the infrastructure maintenance that is required to maintain an STP, the replacements of the spares and other components, the manpower that actually is required to run an STP, the chemicals and the consumables that are required, and of course the sludge production, what happens there, and finally the electricity. Of course, in whose scope it is, whether it is taken by the government or the party that is going to construct STP, that is immaterial here. But when we look into the overall pie, it's very clear that electricity requirement for any sewage water treatment is going to be very, very significant. And we got to understand that how we are going to manage this electricity better, and then how do we make sure that this component of the electricity comes down as far as the overall OPEX is concerned. So this is where we, in fact, talked about the waste to value concept for one of our plants here. What has been constructed at Delhi called Coronation Pillar, which is in fact one of the largest sewage treatment plants today in the country, of 318 MLD capacity, which was inaugurated very recently. And this is basically an anaerobic, aerobic, and oxidation process with biological nutrient removal. In fact, the phosphate removal. Actually, so this is the conceptual view of the plant, but then there are some pictures which are taken just to show what are the various components here. At the one in the bottom towards the left is basically the digester, which is basically used for generation of the electricity here. I'll just come to that part. And of course the gas storage facility, what we have for the biogas that is getting generated here. So that is a kind of a concept towards the waste to value. The reason is, when we look into the regular wastewater treatment plant, which we call, let's say, as a A2O plant. So we have the pre-treatment zones here, and then we have the aerobic zones that is indicated here. And after the aerobic zone, we have the sludge handling part here. So the sludge gets thickened, and then finally we push it through the centrifuge so that the solid sludge of 20 to 25% concentration is eventually is available for disposal. So this is a typical wastewater treatment plant. Now, if we have to make this plant, somewhere where we can maximize the energy utilization, because that's the factor which we are seeing from the operational cost, which can definitely be reduced, and also to push the whole solution towards the circular economy, it's also important to understand how we can basically, factor in the energy management point here. So that's where we can, in fact, think about pushing the sludge into an anaerobic digester, and from where we can actually have the biogas getting generated. And the biogas can be treated and eventually pushed into a gas engine, which is going to generate the power. So all the parasitic load of the plant, it can be basically used by the sludge that is getting generated, and then with the gas that is getting produced. That's an amazing, output that we can achieve. Many countries are doing it, and we have also started now implementing this whole concept more. But it's all the more important that irrespective of the capacity, it's a huge plant, but even if a small plant we have for treatment, even that plant should be able to move towards the energy neutral solution. Then that is an icing on the cake. So there are all the concepts of circular economy, which is basically the reuse, the recycle, and reduce. So everything is actually the part of the solution that we have put together here. To summarize this whole flow sheet, we can think about a primary clarifier, the aerobic process, and finally a digester, gas cleaning system, and sludge thickening system, and finally the gas engine, which we can think about as the core components of this whole solution. So the parasitic load today is around 7.7 megawatt, which this plant consumes, out of which around 3.2 megawatt can be produced just by treating the sludge, and then supplied back to the plant, so that the overall energy requirement of the plant can come down substantially. So that is the way in which this solution is going to be very promising, and that's the waste to value, solution in the circular context of what we can essentially talk about, which exactly is an operating plant live in our country. Now the question here is that all that what we can do? or is there a way to basically improve the situation further? I mean, there are multiple approaches to that. We can in fact look into the different ways in which we can maximize the overall energy utilization and take the plant from today from wherever it is towards the energy neutral solution, because there is still a gap of about 4 megawatt, and we need to basically understand how do we bridge that gap. There are multiple ways in which we can do it. Solution improvement is possible through all these steps. That is essentially has been talked about. Basically, if you look into the process benchmarking, which unit operation has to be used for which purpose, how do I basically make sure that a purpose is met with minimum energy footprint, could essentially the part of the process benchmarking approach. Process intensification is about the reducing the energy intake that particular process demands, and then how do we make it more economical in terms of energy requirement. At the same time, it should be able to deliver the output what the regular process will be able to do. Now, the process innovation is a big gap that has to be basically addressed through the technology innovations. Now, there are technologies which are talking about microbial fuel cell, which is again to be sustainable, to be something which is a reliable technology. It takes time for that technology to mature. Biohydrogen could be one such thing, and there are multiple ways in which we can, in fact, achieve that energy neutrality by investing and then trying to understand things better. Process optimization is all about the digital solutions which we are consistently using across the spectrum, and how do we basically bring the digital twins in order to manage the process better, in order to improve the overall performance of the process better, is the process optimization part. Just towards the process intensification, I just wanted to share one last slide here. This is where we came up with trying to understand which is that unit going to consume maximum energy. Of course, when you talk about the sewage water treatment and the aerobic system, the blowers are the power hoggers there. So that's the one, they are the ones which are going to take maximum amount of energy given the sewage water treatment or any aerobic treatment for that matter. So this is where we came up with a new reactor, which is a hybrid solution, which uses both attached and the suspended growth combination in order to give that energy efficiency better. So basically, we could kind of understand here and demonstrate that how the quality of the effluent with this reactor could be improved. The footprint reductions was better. The power consumption improved significantly. The sludge reduction was possible to a large extent. And of course, the main important part of the capex and opex was significantly, better with this. So that is the process intensification which we have been working, and this reactor we have developed in order to bridge that gap. So basically, I wanted to conclude my talk with the limited time left now. That we have to consider the 4R concept in our water solution, and that should not be in isolation just in terms of treating the water, recycling the water, reusing the water, but also the concept should be expanded further to the energy part, and then we got to understand how the waste is getting managed. At the same time, it's more important today that we are using membranes, for instance, the RO membranes, the ultrafiltration membranes, electrodialysis membranes for various applications. What will happen to them after they are used? That should not be something which should go into the landfilling at the end of the day. So the totality is very important when we talk about the water solution, that every component should fit into the definition of the circularity there. So the significant advancements is possible. There's a lot of gap for research, and we got to in fact understand how to fill that gap in order to drive the solution towards energy neutrality and finally make every solution energy positive later on. With that, I just wanted to conclude my talk here, and thank you so much for giving me this opportunity.
Thank you so much, Dr. Vijaysai. It was wonderful and very informative, especially in the area of wastewater. So, yeah, with that, we'll take up the